So thank you very much, Sylvia. It's a pleasure for me to be here and to spend this day here. So my talk is, the title is written here, but what may be an important word which is missing in this presentation is image restoration, because my subject will be really dedicated to image restoration and how deep neural network unfolded scheme can be used. It's okay. Okay. No, but it's okay. And so how can we use unfolded scheme in this context of image restoration? So in the first part of my talk, there will be no deep learning, because in the deep learning we consider we need to use some standard image processing and some standard variational approach. So the first part of my talk will be dedicated to basics in image restoration. So, and it will be also the opportunity to introduce the notation I'm going to use during all these presentations. So first, in a lot of image restoration problem, the first step is to consider, oops, sorry, the first thing, do you have some? Okay, no, it's not a problem. So the first thing is to have this direct model, z equal x bar plus epsilon. So x bar is going to model the signal in which you are interested in. So typically an image. You want to recover an image in astronomy, in microscopy. The image, for instance, is the one on the top. And so you want to recover this image in order to do further image analysis, such as segmentation, in order to extract parameter in terms that the doctor, that the biological researcher can extract this information. And so the problem is that we do not have access to x bar, but we only have access to z. And z is degraded by these two perturbations, a and epsilon. A is a linear degradation, and epsilon is typically a stochastic degradation. So I'm going to show a very standard example of A, which is linear, and that you can encounter in many image restoration problems. So here I written A, x, as a convolution. I don't know if some of you are familiar with convolution. It's a filtering operation. I'm going to show you example on image of what is going to be the impact of performing this kind of convolution. So typically you have x, and you perform a convolution with this filter. And you will obtain this blurry image here. If now you change the kernel, you see that the blur is not exactly the same. And so it means that the image you are going to degrade, to process can change according to this linear A, but also according to the noise of it. And our goal will be to recover this x bar by using this information of z. If you have just phi as a degradation, it's a bit simpler because you can invert it quite easily. But when you have the action of phi, which is mean A plus noise, the task is much more complicated. And it's the reason why in inverse problem, the standard minimization problem we are going to consider is the following. We have this data fidelity term, which is here to say I want to find the x close from my observation z, but close in which sense? In a sense in a norm, here in this context L2 norm, but in a sense that ax minus z will be small in L2 norm. But if I just do that, it won't be sufficient, because if I have noise, if I just minimize this L2 norm, I will amplify the noise due to the ill-posed problem we have behind. And so a way to thank you very much. A way to improve the restoration is to add this penalization here. And this penalization we will see, can have a lot of different forms. So the most standard one is the one which is called Tikhonov penalization, where you have X, you apply a filter, as I presented before, but a one which is going to smooth the image. And then you apply the L2 norm on it. And this leads to a L2 minimization problem plus the L2 penalization here. So everything is smooth, and you can even derive the closed form expression for this minimization problem. So that is nice. And this is the kind of restoration you can obtain. So you see, it's a bit better. You are able to obtain sharper edge, but still we are not completely convinced by the result. But, by the way, it is the first way to start with this two-term minimization problem, data fidelity term plus penalization. Now, I would like to introduce a concept which is very important in image processing, and I am going to motivate it by two different ways. On the first part, I'm going to motivate it by using wavelets, and on the other part, I'm going to motivate it by what is called TV, but in a 1D example. So I'm going to motivate it by these two different situations, but at the end, we will introduce the concept of L1 norm and see how it goes in our minimization problem and why. So the first thing is introducing wavelets. So some of you familiar with wavelets, or is it the first time some of you are familiar? So the idea, let's say I'm going to introduce it with the filter bank implementation, because I find it a bit easy to introduce like that. So the idea is that you are going to have the original image, and you are going, for each row of your image, apply either a low-pass filtering or a high-pass filtering. So the low-pass will smooth the image, and the high-pass filtering will extract the high frequency, and so the contour, typically, of the image. And so you do that for each row, and then you perform a decimation. So you take just 1 over 2. And you do the same for the column, and you obtain this kind of decomposition. I will show you a result. And then you take the low pass, it will give you a smooth image, and you reproduce it on this smaller image. And so typically, so typically, you obtain this kind of representation. I don't know if it's very clear, but you should imagine the same splitting than here. Here, you have the vertical edges. Here, you have the horizontal edges. And here, you have the diagonal one. And here, you have two different kinds of resolution. So what appears here? You see that you have the same image, but one is much more sparse. You know, when it's black, it means that you have 0 coefficient. So it means that you are able to represent the same image with the same number of coefficients, but in a sparsest way. And so once we have remarked that, the next step consists in saying that, okay, because it's sparse, and if we do a wavelet decomposition of the noise will spread out all over the coefficient. A good way to remove the noise is to take the image, perform a wavelet decomposition, threshold every coefficient below a specific threshold. So typically here you have negative and horizontal threshold. In blue, if it's the action to do nothing. And in red, it means that between minus lambda and lambda, it will be 0. Else, you take more or less the same value. This is called the soft thresholding. If you do that on this image, you remove all the noise, and then if you do an inverse wavelet transform, you obtain the original image without noise. So what is interesting behind that is that this soft thresholding operation that I represented here can also be written as a minimization problem. Actually, this thresholding operation is the solution of minimizing a L2 norm plus lambda L1 norm. So if you consider each wavelet coefficient, it means just for each coefficient, you have a square term, and here the absolute value. You do it for all the coefficients. And so solving it for one coefficient is doing this operation. What is interesting, maybe more, is that this operation, but we will explain it later, is called a proximity operator. And we will see how it is useful in image restoration. And the second thing which is interesting is that now this whole procedure is also a proximity operator of a specific function, which is the proximity operator of lambda L1 norm of psi of this operator psi. Or in other terms, minimizing the L2 norm plus lambda L1 norm of psi x. And so this operation is just the operation to wavelet decomposition, soft thresholding, and inverse wavelet transform. And that can be written like that. So keep in mind, once again, that doing this denoising is the action of minimizing a data fidelity term and a penalization. So then the second approach is not using wavelet transform, but it's in the context of, let's say, TV or pot model, which is going to be associated to L0, but in the context of 1D. We want to denoise a piecewise constant signal. And the question is, how is it possible to denoise such a signal? What I've written here is still the same. I'm going to minimize a L2 data fidelity term plus a penalization, still the same. A norm, I did not specify yet what is this norm, and a linear operator, psi. And I'm going to assume that this psi can be written as a convolution, as it was for the blur at the beginning. And we will see how it's going to impact the effect of the norm and the effect of psi. So first, let's consider a psi, which is just 1 minus 1, so a finite difference filter. And let's consider the L2 norm. So you see, you are going to have this smooth estimate. So I'm not sure if it's clear, but in light gray, you have the noisy signal. So I'm minimizing it, where Z is this noisy signal, and I obtain the red one, while I would like to obtain the black one. So it's not so bad. Here it's with another regularization parameter lambda. So this lambda will affect the smoothness of the solution. But okay, it's not bad. But if in a physics experiment I'm interested in this discontinuity, I'm not able to coach them. So it's a problem. So second solution, I'm going to replace the norm, but I keep the same filter. So I'm either consider the L1 norm or consider the L0 norm. So if I'm consider the L1 norm, you see, it starts to be nice. I have the discontinuity. I'm able to recover more or less the good change point location. But I have this little bias. And sometimes this little bias is a bit problematic because you see here, you almost miss it. And the way to coach it is to replace the L1 norm by the L0 pseudo norm. By doing that, you are going to avoid this bias that you have a bit everywhere. The problem is that this one is convex smooth, this one is convex non-smooth, and this one is non-convex. So you have different level of complexity. So in this very specific example, it's nice because you have a very efficient algorithm in order to solve this specific problem, but in general, it's not the case. And when you deal with image processing, even if you could be interested by L0 norm, you do not have an algorithm dedicated to that. Yes? Yes. I'm not sufficiently familiar with all the reference about it. I know that you have this this work where you estimate the support and you can, but I don't know if the recovery guarantee are as good as the one with the L0 minimization procedure. But the point is that if you know how to solve the L0, it's simpler. So, and I should say also that in 2D, it's also more difficult because in 2D, it's difficult to estimate the support and between, because here it's easy because you estimate the 2 points and between them you can re-estimate it. But in 2D it's much more complicated to identify where is the change, where is the uniform part, etc. So you see the extension to higher dimension is a bit complex. Okay, so this was the second motivation of L1 norm. So I hope you are convinced. And like that, we can continue. Maybe the last thing is about the impact of the filter psi. Here, there are 2 examples. So I'm still minimizing the same minimization problem, but here I'm just changing not the norm, but the filter. Here it's the first order filter, and here is the second order filter. And you see that you are not able to recover the same class of signal. This one is piecewise constant, this one is piecewise linear. So this is typically a kind of signal we encounter in a physics experiment called stick slip, and where you have exactly this kind of signal, and so be able to recover it with this minimization problem is nice because it's a strongly convex problem. We can derive very efficient algorithm, and so for some experiment in physics, we have a nice result in few iterations. Okay. So now let's go back to the image restoration problem. So you have the data fidelity term, you have the penalization where psi could be the wavelet transform, could be the horizontal and vertical finite difference, and could be a large, several other filters that you can encounter in the literature. Non-local TV has been developed, several of them have been developed. TGV, which can also fit this framework, etc., etc. On the other side, rather than solving this one, people solve this one. So you see the psi is moving the data fidelity term by considering the adjoint of psi. So in the case where you are in finite dimension, it corresponds to the transpose. And actually, at the beginning of this image restoration framework, people did that because it was simpler in terms of optimization to solve it. I will explain it a bit later why. And so you have these 2 formulations. One is called the synthesis one. The other one is called the analysis one. In some cases, both are equivalent. So typically, if you have psi which is orthonormal, you can have the equivalence between both. But in general, it's not. And so you have the 2 formalism, and some people prefer solving one. Some people prefer the other one. The sparse coding framework is associated to this one. And here it's another framework where you have TV and all this derivative, which is more familiar. So, but in terms of optimization, it will change a lot. Before going a bit further, I would like to conclude this first part about the evolution of image restoration and about the impact of the penalization with this illustration. So maybe you remember the result of Tikhonov. I should have added here, sorry. So the original, the degraded. So here, it's if you consider wavelet. Actually, it's a wavelet a bit improved. It's a tight frame called dual tree transform. And you see that, okay, the performance are a bit better than Tikhonov. Then, it's the result with TV. So TV is an analysis formulation where you have the horizontal and vertical finite difference. And it's very typical from this staircasing effect that you can see here. And with this TV, what I did is I applied it. So when you have a color image, you have a red, green, and blue channel. And so I just apply TV on each of them. But then you can imagine to have better penalization where you combine all of them. And you can even improve better filtering than just TV. And so it's what I did here and called non-local TV. but it's still the framework that I've presented here, so this one. And so you see that from the degrading one, we were able to do better and better. But what you will see is that it's still possible to do even better, and thanks to neural network. So, but before going into the detail, I'll show you some results. But in order to show this result, it was I needed to implement some algorithm. And so I'm going to detail the kind of algorithm I'm considering to minimize this non-smooth problem. So some of you are very familiar, some of you are maybe less familiar, so I'm going to just recall some basic. So in order to deal with non-smooth function, we can just consider the standard gradient. And so we need to have recourse to the notion of subdifferential of a function. So if f is the function, we will call the subdifferential this quantity. And this quantity so is defined like that. And here is an illustration. So you see this term is represented in red. It's going to correspond to this red plot here. In blue is the function f for which we want to compute the subdifferential. And so here is u is going to represent the subdifferential. And so you see that according to the several value of x you are going to consider, the subdifferential is going to take different value. So typically, if you are on the negative part, where the function is typically a quadratic function, you will have so the question is what is the slope of this red plot? And so you see that the slope is going to be negative, and so it's going to have this shape. Then when you go to 0, you can see that you have different plot of the red function that can stand below the blue one with different slope. And this is the reason why you have all these points here associated to the subdifferential. So in the point where you are non-differentiable, u is not reduced to a singleton. And then when here it's associated to an absolute value on this side, then you see that the slope of the red plot, if you plot it below, is constant. And so that is the notion of subdifferential, and we need it when we do non-smooth optimization. The first thing is to consider that, okay, a basic and important concept that you need in optimization is this rule, is the Fermat rule, saying that x hat belongs to the argmin of fx, because you are interested in this x hat when you solve a minimization problem, typically for image restoration. And so that is equivalent to finding the 0 belonging to the subdifferential of f at x hat. So that is the first important point. And the second one is that the basic idea is to do not a gradient descent, but to do a subgradient descent. So the subgradient descent is the following. I take, okay, so I have an initialization starting point, and then I'm going to run iteration. The iteration will be of this form. I take xk minus uk, where uk is the point in the subdifferential of f at xk. So that is a subgradient descent. It's an algorithm which is called the Shor algorithm. It works. However, it is very sensitive to the way that you are going to choose the step size. And in particular, numerically, it's very complicated because you need to select the step size decreasing, which means that at a point you are going to converge numerically, but just because your step size is too small. So it's complicated to implement numerically. So in order to still deal with non-smooth optimization, but in a context where okay, you can be able to design efficient algorithm, we need to have to use another concept, which is the one of proximity operator. So the proximity operator of a function f is the minimization, the minimizer of this L2 term plus the function. Okay, maybe if you remember the beginning of my presentation, I already present 2 procs, even 3. Remind where they are. I presented 3. The first one was this one, the proximity operator of the L1 node, which is this one. The second one was this one, so meaning that doing a prox over Z will give you this denoising solution. And the last one, and several other examples, are this one, the solution of this minimization problem, depending on the choice of the filter and depending on the choice of the norm. Okay? So I presented several of them, but the key point with proximity operator is that you have some closed form expression, and some of them, many of them are listed on prox repository, but a lot of them does not have a closed form expression. And this is the key issue, because if you do not have a closed expression for the proximity operator, you need to run sub-iteration to do it. But let's consider first that we know the proximity operator, and let's see why it's interesting. So P, let's say that P is the proximity operator of F at the point X. And so you have this characterization. So maybe we can just write Y. So this is the definition of the proximity operator. I write here okay, maybe we can remove this one, but just here is the Fermat rule, and here is this result, which leads to this equation. And it's interesting to notice that doing the proximity operator at xk gives you this xk plus 1, which is also equal to this subgradient descent, but not in xk, in xk plus 1, which is not an explicit gradient descent, but an implicit gradient descent. And this is the key difference by just doing a subgradient descent and a proximity step. It's in the point for which you take the subdifferential. So now, I say that for many function f, you have the closed form expression for the proximity operator, which is nice. So it means that we can run the proximity point algorithm. I apply prox several times, and I converge to my solution. The problem is that computing the proximity of a sum of 2 terms, as we are interested in image restoration, so the data fidelity term and the penalization, is much more difficult. So it's and it's typically the kind of situation where you do not have closed form expression for the proximity operator. So in that case, you can't use just this recursive algorithm where you apply several times the proximity operator. Another complicated task is when you have f composed with a linear operator. But you will say, okay, but you show us the example of wavelet denoising. Yes, it's true. But for wavelet denoising, it works because psi is an orthonormal wavelet transform. But in general, for non-orthonormal wavelet transform, you do not have a closed form expression. Yes? Yes. Okay, so that is a good point. Just exactly. So in all the examples that I have motivated right here, it's the penalty term, true, and so this is the proximity operator. But if you remember, in the beginning of the presentation, I talk about inverse problem where you have a data fidelity term and the penalization, and so what is going to change is that here you will have the A. And so in that case, it's not anymore a proximity operator. So then you cannot just define it as a prox, but it starts to be a sum of 2 functions, and you want to minimize a sum of 2 functions. You are going to use prox, but the minimization by itself is not the solution of a prox. Okay? Sorry, could you repeat? Yes, it's exactly that. So F1 is going to be, sorry, the data fidelity term here, F2, the penalization. But right now, in the example that I gave to you, F1 was reduced to an example without the A. Yes, still, yes, still, yes, F1 was 0, or if, it depends of what, okay, okay. So now the question is how to compute the proximity operator of a sum of two functions. So why? Because you are interested in this sum of minimization of two terms, the data fidelity term and the penalization. So in the following, we are going to assume that F1 and F2 are convex. So I forget it, yeah. But, and then F1 and F2 are either differentiable with a Lipschitz gradient or can be computed by its prox. So making reference to the previous slide. And so here you have several schemes which are well known in the literature. The first one, so each time you are going to build this sequence and F2 are smooth, you are doing the gradient descent by computing the gradient of F1 plus the gradient of F2. If you know how to compute the proximity operator of F1 plus F2, you are going to run several times the proximity operator of the sum of the two functions. If you don't know how to compute the prox of F1 plus F2, but you know the prox of F2, and you know how to compute the gradient of F1, you can use this scheme, which is called forward-backward. So gradient descent followed by a proximity operator step. You can have Pisman-Rashford algorithm, where you activated F2 and F1 by the proximity operator in this way. And Douglas-Rashford is the same, but you activated the prox in a different way. So you have some assumption to satisfy if you want to have the convergence of all these schemes. But in the context of smooth, at least you have one smooth function, all are going to converge. And for this one, you need that both are smooth, else you can't compute the gradient. Now, if you have a function f1 plus a function h2 composed with a linear operator, and here you can see that it's very close to the minimization problem I defined at the beginning with the data fidelity term and the penalization with the wavelet transform of the finite difference filtering. In that case, it starts to be complicated because sometimes we don't know how to compute the proximity operator of this term. And so you have several strategies in the literature to deal with that. Either you go onto the dual, so you are going to compute the conjugate of f1 applied of minus psi star plus h2 star. And the last formulation is the primal dual algorithm. So here is a more general writing where you have a sum of three terms, and the primal dual algorithm is the following. You compute the gradient of a function, and then you compute the proximity operator of f2 and the proximity operator of the conjugate of h2. And you see that the function psi and its adjoint are activated in this iteration. So my point here was more to say, okay, if you have your minimization problem, if you are non-smooth, use proximity operator is a good solution. You have a lot of configuration where you have a closed form for proximity operator, but it's not true for all the functions, and especially when you have a sum of two functions. In that case, you need to have recourse to iterative procedure, and it could be forward-backward, Douglas-Rashford, forward-backward, Pisman-Rashford, or it can be primal dual strategy, depending on the property of your problem. But all these schemes are going to converge. And all the results I presented before in image restoration are based on this algorithmic procedure. And so when you do optimization, then the main objective is to try to find this minimization, the minimization of this f1 plus f2, in the fastest way. And not just on small image, but on huge image or on huge data set. And so that is very challenging, and it's still very challenging. But now, for many years, we try in image restoration to change the property of F1, of H2, in order to improve the result. But at a point, we are a bit stuck, as I saw on as I presented on the image restoration. And so it's where now the neural networks comes in order to help still continue to improve the result. And we will see how this kind of algorithm can help us in understand, in design, neural network. So, first, I would like to remind a few things. So this is the direct model, so AX bar plus epsilon, or D is going to model the degradation here. Here is going to be the data fidelity term plus penalization. Here is going to be the sequence. And then at the end, once you even find the minimization problem, you still have this lambda to select, which is often a tricky task. So when you do standard inversion, you need to do all that. And what's, in a sense, learning say is that, okay, replace everything, just have a database, put it in PyTorch, and solve that. Okay, so in a sense, it's very satisfactory. But let's see what we can say more about that. So first, few things. What does mean design a neural network? So first, you need to design, to have a data set of data, and the data you want to predict. And you need to design a neural network. What is a neural network? A neural network is typically weight, activation function, and bias. And so for each layer, you have this weight matrix, this activation function, which are nonlinear, and bias. And when you do deep learning, you are going to find the parameter theta, so typically the weight and the bias, in order to minimize a loss function, in order that the input data fits the output. So in the context of image restoration, what does it mean? We have, in terms of database, the degraded data and the original data. So it means that first, you need to create it. So it means behind, if you want to create a good database, that you need to know the direct model. So it was hidden, but actually, if you want to create the database, you need it. And so you need this expression. Second, you have this training stage. And this training stage, you can consider a d theta, the neural network that you prefer, UNet, etc. And then you are going to train the theta in order to minimize this training set. And a good network, a network will be good if d theta applies to this degraded data, give you an image close to the original one. So this is the standard architecture, typically UNet. You can apply it directly to the degraded data or to the pseudo-inverse of it, and you will obtain good results. Sorry, I'm going to skip the two slides which were not useful. So now I'm going to explain how what I explained during the first part of my talk can be useful to design neural network. And I'm going to start with the synthesis formulation. You have the data fidelity term, you have the penalization, and then, if you remind several algorithms that I presented to you, so it's non-smooth, so I can use the prox for this one is smooth, I can use the gradient. So typically I'm going to perform the gradient of this one followed by the proximity operator of this one. This is the forward-backward scheme. So the gradient of that is this operation where h is a psi star, and followed by that. Okay, we can reorganize this iteration. We have this term, and the prox is just the same return. And what we can observe is that actually, here we have an activation function, a nonlinearity. We have weight, and we have bias. So So what we can observe is that just by doing forward-backward iteration on this simple example, we obtain the architecture of a neural network. But what is the difference between a standard scheme and a neural network is that the weight here are learned. And okay, this is in the synthesis formulation, and I used to do a lot of analysis formulation, so we try to do it for analysis formulation, but before explaining that, I would like just to notice few remarks that are interesting, is that you can refer to the work of Combet and Pesquet. Most of the activation functions are proximity operators. So it's nice. So it means that when you design a neural network, you replace the activation, you say activation function, but you can say proximity operator. And in terms of optimization, you start to have an interpretation of that. And then you have some nice properties. So typically, if omega is bounded linear operator, bk a vector, and eta k a proximity operator, which is 1/2 averaged operator, then the neural network, you can derive tight Lipschitz bound, and it allows you to evaluate the robustness of the neural network. So I presented before, I don't know if you have all in mind, but if you do the same thing for the analysis formulation, you are able to derive, for instance, convexity iteration, where you have the gradient descent step for this. Then you have the linear operator of H here and here, and the proximity operator of step of L1 is the proximity operator of the conjugate function of L1. And you see that, okay, maybe it's a bit more difficult, but not really. You still are able to build this architecture, where you have the activation function, the weight, and the bias. Which means that, once again, you are able to design a neural network. The specificity we are going to do that is that, for the moment, if I'm just applying this network, it's just convexity iteration. And so I'm going to converge to the same solution that I presented before. If I select the step accordingly to standard, the step size of the algorithm, the regularization parameter is exactly the same result than before. The way we could try to improve it is to use the way that it works for neural network. We can start to learn parameter. And what could be the parameter we can learn? So A star is the direct model, so we can assume that we know it and we can keep it. But H, what is H? H is the dictionary. It's the analysis, and maybe inside it, if we just do horizontal and vertical difference, it's not sufficiently informative. But if we learn it, it starts to be more informative. And so, if now we start to learn H at each iteration, and maybe allow a bit of flexibility from an iteration to another one, like for those who are familiar, when you have let's say image restoration problem, sometimes in the iteration you can move the regularization parameter. Here it's the same. In a sense, you move a bit how the way the dictionary is going to change from an iteration to the other one. And so it's what we are doing. And so I'm going to, okay, so it's the first work we did just for the first work we did on this subject. We rederive all the gradients with respect to the parameter, but now we use PyTorch. And PyTorch does it for us, and the results are as good. So, and this is the kind of result we obtain on this very simple data set, because it's nice to see the difference. So it's the digit, the noisy one, TV, non-local TV, it works well, but you see actually this is 2 neural network, and this is the method proposed. So we see that it starts to work well, and maybe as good as IRCNN, and better than the state-of-the-art method. So allowing this flexibility in the dictionary learning help. This one, IRCNN, is, I have few slides after that about it, but the idea is like a plug-and-play method. You are going to introduce an auxiliary variable, and you are going to solve the, let's say, the least square problem, and then to plug a prox. If you have just a CNN, this one is very close to a CNN, except that it's based on wavelets. But it's just some result. I have other than that. And it depends of the size of the database also. So that was the first result, and in the next one I'm going to show, I think now the results are, I can say, are much more accurate in terms of size of the database we used to training the number of parameters, so I prefer developed, comment the result on the second part. So this is the good question. For this one, yes, but what I would like to mention of this work is that it was an oldest one. So we redo everything in PyTorch in the new one, and I'm sure that on the new training result I'm going to show you, we make sure that we train on same data set, or the number of the parameter on the neural network are the same. I'm going to comment it later. And so here, so can I use 5 more? So now the question was, okay, I have this primal dual scheme, I unfolded that, I learned dictionary in a sense with that, it works well, okay. But so I can use another algorithmic architecture, try to do the same. Does it improve the result? Are the results the same? Is a fast algorithm learn better or not? Because if so, it's nice for the optimization point of view, because it means that developing fast algorithm can help in the learning. So we ask this question in a very specific context of denoising. Why? Because denoising is this context where you have the L2 data fidelity term plus L1 with dx, if you want. And because you have the L2, it's strongly convex. And in the strongly convex case, you know that you can derive fast procedure based on the strong convexity constant, etc. So we play with it. And I have just 5 minutes, so I'm just give you the main idea of that. We use, so if you want to minimize this problem, you can't use forward-backward, because you can compute the gradient, but you can't compute the prox of that. So the typical way to do that is to go in the dual. You obtain this minimization problem, you compute the gradient of it and the proximity operator of it. And in the dual, you can use forward-backward, or you can use, let's say, FISTA. So it's an inertial version of forward-backward, which is faster. The second procedure is to use either Chambolle-Pock iteration, very close to the one I presented before, or an accelerated one based on strong convexity. So which means for this problem, I have 2 algorithms, forward-backward, or FISTA, which is the accelerated one, or Chambolle-Pock with strong convexity. And so I have 2 algorithms with 2 accelerated versions. What probably you can trust me, but is really similar, is that you can also write it in you can write similarly in this way with activation function, weight and bias, both for forward-backward, FISTA, Chambolle-Pock with strong convexity. Every algorithm can be fit this scheme. The other interesting point is that the activation function of the proximity operator of the conjugate of the L1 norm is the activation function which is called the hard tangent hyperbolic. So it's nice because when you implement, you can use just this activation function. And so you do that for all the scheme, and here are the results. So this is the result in terms of training loss and in terms of PSNR. So we train on the similar data set. We train with neural network for all the one we developed, and for the black one is IRCNN, is the one I presented before. And for all this network, we train with the same number of parameters in the network. And so what we observe is that, okay, in red, oh sorry, the legend is not here. In red is Chambolle-Pock, and in yellow is the forward-backward scheme. FISTA is better than forward-backward, and Chambolle-Pock with strong convexity is better than Chambolle-Pock. And also in terms of SNR. And what we observe is that Chambolle-Pock with strong convexity seems even better in terms of SNR performance. And you see, if you compare to the standard neural network, we perform better. And it's more stable. And here are the kind of results we obtain. So with DN-CNN and with the proposed one. So you see with the proposed one, it's very close, maybe a bit better. And it's much better than what we were able to obtain with standard variational approach. The same here for maybe Noiser dataset. Here is some general comparison where we compare. So here is the number of layers, and here is the number of features. Is for FISTA, Chambolle-Pock, and Chambolle-Pock with strong convexity. So the faster one are this one and this one, and you see that FISTA, when it's more yellow, it's better. So FISTA is better than ISTA, and Chambolle-Pock with strong convexity is better than Chambolle-Pock. And then in terms of robustness, we see that the more you are deep, the less you are robust. And but actually, I would like to take some carefulness with this result, because the way that we compute the bond was very not very nice, because we compute the product of the norm of each weight of the network, which is not tight, as it's a really huge upper bound of the neural network. And in that case, all are equivalent. And so I would like just to finish with this point. The last, so here we design a denoiser. We design a denoiser with this unfolded scheme in a similar way that in the context of image restoration, but just for the task of denoising. And so what I'm going to do is to plug this denoiser into the forward-backward scheme, which say, typically, I'm doing, I want to minimize this problem. I'm doing the gradient over it, and then I should compute the prox of R. And the prox of R could be just TV, or could be the denoiser I derived before, or could be another neural network. Okay, it's just the action of the denoiser. What you can show, what has been shown in the literature, is that the convergence of xk is going to ensure if the denoiser is firmly non-expansive. Most of the existing denoisers are not firmly non-expansive, so you can impose it. It means you can take a neural network, impose it non-expansivity, or in another way, you can build it to be a prox, as we did before. So I would like to make some precaution, because in our case, the D is going to vary from an iteration to another one. So we cannot have the interpretation as an exact minimization, the resolution of a prox, but we are not really far. And so recent work make it, it's time to finish. Perfect, I'm done. And so okay, I'm going to skip this part. And this is the kind of result you obtain. So if you do plug and play, where you plug a neural network, a standard neural network, and if you plug the one I presented before based on Chambolle-Pock with strong convexity. So the results are very close, and you see that it performs quite good. And just to finish this part, here is the evolution of the result during the time from Tikhonov to DTT to TV, NLTV, their unit, and SSCP. So this is the last kind of result. And you see that, okay, for this kind of degraded data, okay, I think now the results are very, very good. But it does not mean that we have nothing to do, because in image restoration, it's an, let's say, easy example. We know the blur, the noise is not too high, so we still have work, I think, but still, it's okay. Just that is the kind of result we obtained during my PhD, so almost 12 years ago, and is the result we obtain now. It's quite nice to see the evolution. So I would like to conclude by saying that unfolded schemes, oh yes, important comment, allow to learn better with less parameter, because the thing I didn't say here is that we learn similarly with 300 times less parameter. So we obtain the same performance with much less parameter. So that it starts to be interesting. If by using knowledge about proximity operator, we need less parameter, which means a less costly training. Then, faster scheme can help in the design of efficient architecture, which is the case of strongly convex Chambolle-Pock. And plug and play with SCCP, very good performance, but it's still there are still challenging questions, especially when you have a huge amount of data, where you have nonlinear degradation, for instance, for semi-blind restoration, because you have a lot of problem where you know partially the A, you don't know it completely. So there are still plenty of questions, but it's also nice to see that at a point we start to having very good results. Here are a few references, and there is an extension of one with Audrey Repetit, which will be ready very soon with this plug and play with Chambolle-Pock with strong convexity. So thank you very much.